Beneath the visible world lies a hidden ocean of energy. Every particle, every atom, every moment of existence, a ripple on this invisible sea. This is quantum field theory, or QFT, the language of the universe at its most fundamental level. Where classical physics saw solid objects and empty space, QFT reveals something deeper. There is no emptiness, only fields, endlessly vibrating, endlessly alive. Before we get too deep into this topic, be sure to like this video and subscribe to the channel. This helps to bring more valuable content to the platform for your knowledge and understanding. Remember, knowledge is power. Now back to the episode. At the dawn of the 20th century, physics was fractured. Max Planck, in 1900, discovered that energy was not continuous but came in discrete packets, quanta, while studying blackbody radiation, Planck, 1900. This single insight shattered classical ideas and opened the door to a new world. Soon after, Albert Einstein explained the photoelectric effect, light itself behaving as both wave and particle. These discoveries formed the seed of quantum mechanics, but something was missing. Physics could describe particles or fields, not both at once. It was Paul Dirac, in 1928, who first merged quantum mechanics with Einstein's relativity, giving birth to the first form of quantum field theory, predicting not only the electron's behavior, but the existence of antimatter. Dirac, 1928. In quantum field theory, particles are not tiny billiard balls. They are excitations of fields. The universe, it turns out, is a collection of fields: an electron field, a photon field, a quark field, and so on, each extending throughout all of space and time. When a field vibrates in just the right way, a particle appears. When that vibration stops, the particle disappears, but the field remains. This idea changed everything. Suddenly, interactions between particles could be seen as interactions between fields. An electron repelling another electron? That's the electron field interacting through the photon field. And in the 1940s, Richard Feynman, Julian Schwinger, and Shinichiro Tominaga refined these ideas into quantum electrodynamics, or QED, one of the most accurate physical theories ever devised. Feynman, 1949. QED could predict experimental results to 1 part in a billion. Each type of particle corresponds to its own field, and these fields can create, annihilate, and interact with one another. What appears to us as solid matter is, in truth, the interplay of quantum waves woven through space-time. Visualize it, an invisible lattice of energy stretching across the universe, rippling with constant motion, even in what we call empty space. This constant jitter is the quantum vacuum, alive with virtual particles appearing and vanishing every instant. These fluctuations are not just theoretical, their effects are measurable. The Casimir effect, observed in 1948, confirmed the presence of vacuum energy between metal plates. Casimir, 1948. By the 1970s, quantum field theory had evolved into the standard model of particle physics, uniting 3 of the 4 fundamental forces: the electromagnetic force, the weak nuclear force, the strong nuclear force, each mediated by its own quantum field and exchange particles: photons, W and Z bosons, and gluons. But one question lingered: why do particles have mass? In 1964, Peter Higgs, François Englert, and others proposed a new field, the Higgs field, a universal medium that gives particles their mass through interaction. Higgs et al., 1964. Half a century later, in 2012, the CERN Large Hadron Collider confirmed the existence of the Higgs boson, a triumph for QFT and one of the greatest scientific achievements of modern times. ATLAS and CMS collaborations, 2012. Quantum field theory is not confined to laboratories or blackboards. Its principles pulse through modern life. The light from your phone screen? Guided by semiconductors whose behavior is described by quantum field interactions. Magnetic resonance, imaging, MRI, built on quantum spin and field resonance, allows doctors to visualize tissues non-invasively. Lasers, transistors, and quantum computers, all born from the mathematics of field theory. Even cosmology relies on QFT, the early universe's rapid inflation, quantum fluctuations stretching across spacetime, and the formation of galaxies. All are described through quantum fields. Despite its success, QFT remains incomplete. Gravity, described by Einstein's general relativity, resists full unification with quantum field theory. Physicists pursue this goal through new frameworks like string theory, loop quantum gravity, and quantum geometry. Experiments such as LIGO's gravitational wave detection and Planck satellites' cosmic microwave mapping give clues about this deeper unity. In 2020, researchers at Fermilab observed deviations in the muon's magnetic moment, a potential hint of new physics beyond the standard model, Abbey et al., 2021. If confirmed, it could rewrite the very fabric of QFT itself. Today, QFT influences cutting-edge technologies like quantum computing, superconductivity, and quantum sensors capable of detecting single photons or molecules. In medicine, quantum-level understanding is improving imaging precision, early diagnosis, and even the design of molecular treatments. And yet, for all its power, QFT remains mysterious. Physicists continue to ask, is the field the final layer of reality, or merely another ripple in something even deeper? The universe is not made of things. It is made of interactions, waves of possibility collapsing into the reality we observe. Quantum field theory teaches us that existence itself is vibration, energy dancing in harmony with the laws of mathematics. And somewhere in that vast field of energy, we find ourselves, observers, participants, and creators of the very reality we strive to understand. As the fields hum beneath the silence of space, one truth remains: everything is connected. Everything is field. If you found this content helpful, don't forget to like this video and subscribe to the channel. Leave me a comment. Let me know what you think about quantum field theory and the very fabric of reality. Join me next time for another deep dive into the strange and unusual world of quantum physics.